Now we'll finish with some more advanced examples. And by advanced examples, what I want to point out is that we might have to actually look at a combination of different operations in order to get from our familiar series to the desired one. So in all of these examples, again, we'll focus on those series centered at 0, so I can use the known ones. So we want to find the Taylor series centered at x equals 0 for each of the following. So let's start with the function f of x equals x over 1 minus x squared. So one thing to think about from what we've seen so far is I know that I can deal with powers of x by just adjusting the exponents on my x values. So my first instinct is to write this as x times 1 over 1 minus the quantity, or 1 minus x quantity squared. So then I can see that my goal is to try to find the Taylor series for what I have in parentheses, and then my last step could be to multiply by x. So in doing so, now I want to focus on this here, and we can observe that 1 over 1 minus x squared is the derivative of 1 over 1 minus x. And now I can observe that I know the Taylor series for 1 over 1 minus x. That is the sum from k equals 0 to infinity of x to the k. So now I can differentiate that series to get the series for 1 over 1 minus x quantity squared. And in differentiating this, my new terms become kx to the k minus 1. And in order to figure out what goes here, because we always have to be careful with differentiation, I want to observe the original series was of this form. So it had a first term that was constant, so its k equals 0 term was a constant, and that, when differentiated, went away. So this has to be bumped up to k equals 1. So now I'm only left with having to deal with that multiplier of x. So now I can say f of x is x times the sum from 1 to infinity of kx to the k minus 1. And as we saw with multiplying by powers of x, what I can do is just adjust my exponents. So x to the k minus 1 now becomes x to the k from adding in the exponent 1 there. So this is my final answer here. I also want to address, though, why we didn't interpret this another way. So often when I do this in an in-person class, it's suggested that in trying to relate 1 over 1 minus x squared back to our known Taylor series, that this is 1 over 1 minus x times 1 over 1 minus x. So, of course, that's a true statement. However, I don't find that to be a helpful statement given my current goal. So from that, we could simply say that, yes, it would be the product of these two sums. But then our goal is to write that as a single sum, as we did above. And the idea here is that this is now hard to work with. And again, we saw why that was hard to work with in our example of multiplying sine times cosine. So I'll just point out this is not a helpful technique or observation for this particular task. And that's why, in general, when you're looking at a function and you want to relate it to one of the known ones, the goal is to try to relate it in some way through either function composition, differentiation, or anti-differentiation, viewing anything as a product of functions that we know the Taylor series for is not going to help us find a single Taylor series. So we want to kind of steer away from that. Okay, another example, consider the function f of x equals x arctangent of x squared. So again, I want to think about the order here in which I want to approach this. And of course, the main thing that jumps out at me is the arctangent, because I have a Taylor series for that. The arctangent of x has the sum from 0 to infinity of -1 to the k, x to the 2k plus 1 divided by 2k plus 1. Now, I then can use that to find the arctangent of x squared, because that I can do with just function composition. So from what we've seen so far, in order to find this Taylor series, I only need to replace x with x squared. And as I have indicated in the past, it's very important to simplify. So I don't want to leave this like x squared raised to the 2k plus 1. And that's especially important because I'm not done with my whole process here. So I can simplify this now by writing this with 2k plus 1 in the denominator, still my -1 to the k in the numerator, but x raised to the 4k plus 2. And finally, to get my f of x, we simply have to multiply x by the series that we found above. And as we have addressed at this point, to multiply by powers of x, what we're going to do is adjust the exponent. So multiplying by that power of x leaves me with the sum from 0 to infinity of -1 to the k, x to the 4k plus 3 divided by 2k plus 1. And again, this now is my final answer. And I want to address a couple things at this point. A common mistake I see is leaving it like we have here in this step. So if somebody were to leave it like that and then jump to trying to multiply by x, there are several mistakes that I see in that process. Some people might change the x squared to an x cubed in there. And of course, that is not going to be equivalent to 4k plus 3. And likewise, I might see somebody change the 2k plus 1 to a 2k plus 2 when multiplying by x. But again, the problem there is because you have x squared in there, you're actually adjusting the exponent by 2 instead of 1. So it's really important to simplify before we move on to the step of multiplying by x. The other thing I want to address here is the order of operations. I first did function composition and then I multiplied by x. If I started by finding x arctan x, so multiplying by x, and then I substituted in x squared, notice that that wouldn't be equivalent to what we're trying to find because we'd have x squared times x squared. You could, of course, then divide by x to get the correct answer, but that's an extra step. So just kind of being careful with the order in which you're performing these to make sure that you really are ending up with the desired function. So if I have another example, let's look at the antiderivative of e to the minus x squared. So again, what I can start with here is e to the x. E to the x has Taylor series, oops, I guess this is actually example 3, has Taylor series k equals 0 to infinity, x to the k over k factorial. And, oops, let me fix this view. Okay, so if that is the Taylor series for e to the x, my next step is to use that to find the Taylor series for e to the minus x squared. Through function composition, I can say that that is minus x squared raised to the k over k factorial for the terms. And then importantly, again, trying to simplify this. So that's negative 1 raised to the k, x raised to the 2k, all divided by k factorial. So now I have the Taylor series for the integrand, and my final step is to actually anti-differentiate that. And in doing so, we can think about, again, what is going to stay the same. So I still have my negative 1 to the k, and I have my k factorial. But x to the 2k is going to become x to the 2k plus 1 with a factor of 2k plus 1 in the denominator. And importantly, the question here is asking for an indefinite integral. So my final answer should include my integration constant. And then one last example, let's look at the function f of x equals x squared divided by 1 plus x squared quantity squared. And something I should have mentioned for all of these, I'm going it through one way that we can find this, but there's often several correct pathways and combinations to look at that we should end up at the same final answer. So if your instinct is to start in a different way, it doesn't mean it's wrong. You could have a sequence of steps that would work starting with your desired first step. So where can I start here? Well, there's lots of places. Again, my instinct is to deal with the multiplication of x squared as my last step, which means I want to do something about finding the function that 1 over 1 plus x squared squared in there. So things to look at here, first of all, we can notice that 1 over 1 plus x is 1 over 1 minus negative x. So if I use my Taylor series for 1 over 1 minus x, I can see that this would give me the alternating version of that. Then if I want to consider next 1 over 1 plus x quantity squared, right? That's kind of similar to the first one we started with. That one had a negative, a 1 minus x. But if I want to think about the connection here, this is negative 1 times the derivative of 1 over 1 plus x. Right, because the derivative of 1 over 1 plus x would involve a negative, which I don't have on the left-hand side. So this would give me negative 1 times, and we need to differentiate this series I found in the line above. So we get negative 1 to the k, kx to the k minus 1, starting at 1 because we lost the constant term. And essentially, because I'm multiplying by negative 1, I can bring this inside here and express this as negative 1 to the k plus 1, kx to the k minus 1. So at this point, I have the Taylor series for 1 over 1 plus x quantity squared. The next thing I might do, if you think about the connection of that to what I have up here, is I have to do function composition again. So I'm going to think of that as 1 over 1 plus this x squared is replacing x. So I take my series that I have on the line above and I replace x with x squared. And again, in simplifying that, the terms now become negative 1 to the k plus 1 times k times x to the 2k minus 2. And at this step, the only thing I have left is what I identified as kind of my last step from the start, and that's multiplying by x squared. So we're calling this function f of x. F of x is now x squared multiplied by the series I got above, which starts at 1. And at that point, what I'm going to observe is that multiplying by x squared allows me to add 2 to the exponent of x. So this leaves me with the sum from k equals 1 to infinity of minus 1 raised to the k plus 1, k, x to the k. X to the 2k. Just adding 2 to 2k minus 2. And that's our final answer. So, like I said, you can consider lots of different ways of getting there, but we should have the same final answer. The other thing I'll point out is, especially in working through the textbook problems, be sure to notice where their index starts, because you might check an answer and think that you got the wrong answer, but in fact it's equivalent to the one in the back. I think a lot of times they seem to re-index it to start at 0. I don't really see any reason to do that in this case. And again, I really encourage getting as much practice as possible. This is not an easy thing at first. You can see this last example in particular had lots of steps. So the more practice you get, the easier this will be. So really taking the time to go through those textbook problems will be important.